Hello friend, in this video we will see that what is meant by vector space and example of vector space. Friend, you are all familiar with two structures of algebra, namely group and ring, and you know that group is a non-empty set with one binary operation and a ring is a non-empty set with two binary operations. The binary operations defined on a one set. Uh, in vector spaces, we have two sets and we have combined them. So we will discuss about what is meant by vector space. Directed line segment. You have seen this in mechanics and geometry. When we consider a vector as a line segment in two-dimensional space, we denote it by order pair, where order pair is a terminal point in a fixed coordinate system. Now, the vector is a Latin word. Its meaning is carrier or traveler. Vector a is an ordered finite list of numbers. It is written vertical array surrounded by a square or a curved parenthesis. On your screen, you can see that how a vector represent. You see that one is like a column matrix where the entries are 2, 4 and 7 and other is like a row matrix where the entries are separated by commas. Both are the vectors. The number or values of elements in a vector are called scalars, and the number of element in the vectors is called size of that vector. So in this example 247 there are three entries and therefore size of this vector is 3. When all the entries are 0, it is called as a 0 vector. Now we see what is meant by vector space. Let V with a binary operation plus be an abelian group and F with two binary operation, we denote that binary operation by the symbol plus and dot, and it is a field. Now we combine these two sets V and F by taking binary operation on these two sets F cross V, and the product of these two sets is again an element of V. If alpha belongs to F and small v belongs to capital V, their product alpha OV or alpha small circle V, we call or we pronounce it as a into or multiplication, but it is not an as usual multiplication. So alpha V belongs to V. If this binary operation or this function if satisfies these four property on your screen, it is called as a vector space. The first property of the vector space is alpha plus V into V, alpha plus beta into V. You can see that alpha plus beta is in parenthesis. So preference goes to the parenthesis term, and if this product is equal to alpha V plus beta V, then first condition hold. Second condition, in the second condition we have taken two vectors u and v and we have multiplied by alpha. When alpha is multiplied by the product of v plus u, and if this product is equal to alpha v plus alpha u, second condition, this is the second condition of the vector space. And third condition, alpha beta into v, parenthesis, that is preference goes to first alpha and beta. So alpha beta first and then multiply by vector. If this is equal to alpha times beta vector, beta into v, and last one property is 1 into v equal to v, where 1 is the unit element of vector. If all these four properties satisfied, then this set is called as a vector space. Remember one thing, this vector contain two sets. One is a vector. So in the structure of vector space, we have two sets. One is V and another is a F. V is an abelian group, whereas F is a field. Now to stress this field, sometimes we write it as V of F. When F equal to R, if we take the F, the unknown field is equal to R, that is the set of real number, it is called as a real vector space. When F equal to C, it is called as a complex vector space. C means the set of complex numbers. Here we have two different sets. F is a field, V is a abelian group. So there are two identity elements, and therefore we denote these two identity element by 0, same symbol 0. And also you should note that the plus is only the symbol of binary operation in both vector space and in a field F. It is not the same as usual we use in a real number, set of rational number, set of integers. So you can define your own binary operation for these sets. Now we see the example of vector space. On your screen, you can see that the set V is an order tuple alpha comma beta, set of all order tuple where alpha beta belongs to F, where we have defined their addition, how to add this order tuple and how to multiply by scalars. Then first property is a closure property, which is as usual addition of two order tuple is again an order tuple, so it belongs to V. And if we multiply by scalar two order tuple, it is again an order tuple, so it is again belongs to V. So both operations we have taken are well defined operation. Now we see how they satisfies the conditions of vector space. On your screen you can see that the first property of a vector space we have taken a group. Consider three elements in order tuple, which we have taken alpha 1 beta 1 order tuple as a first element, alpha 1 alpha 2 as a first element, beta 1 beta 2 order tuple as a second element, and gamma 1 gamma 2 as a third element. And we have added, you can see on your screen how to add. Parenthesis means preference goes to inside the parenthesis system. So we have added firstly alpha and beta terms, and we get again an order tuple alpha 1 plus beta 1 as a first element, and alpha 2 and beta 2 as a second element. Then we have added the third element gamma 1 and gamma 2. So we get the same as on your screen. You can see that this is similar to alpha 1 comma alpha 2 plus preference given to beta and gamma terms, beta 1 beta 2 gamma 1 gamma 2. The identity element of this set is 0 comma 0. We have added this element. On your screen you can see that how to add this term gamma 1 gamma 2 plus 0 comma 0. Again we get gamma 1 and gamma 2. So 0 comma 0 is the identity element of this vector space. Now the inverse of this set is minus gamma 1 comma minus gamma 2. If we add this, we get 0 0. So this is an inverse, additive inverse of this vector space. This shows that V satisfies all the property of vector space, abelian group. Now we see how it satisfies the condition of vector spaces. Consider any two scalars alpha and beta, and we have taken one vector which is denoted by alpha 1 and alpha 2, order pair alpha 1 and alpha 2. Now multiply this component wise multiplication. First we have multiplied by alpha 1 to alpha plus beta. Then we get alpha alpha 1 plus beta alpha 1. And second term of this order pair is alpha alpha 2 plus beta alpha 2. Second property, alpha times alpha 1 comma alpha 2 plus beta 1 comma beta 2, and there is a parenthesis for the vectors. So we have firstly added the vectors and we get alpha 1 plus beta 1, alpha 2 plus beta 2, and then we are multiplying by alpha. And on your screen we can see that how to multiply this, and we get alpha times alpha 1 comma alpha 2 plus alpha times beta 1 comma beta 2. Third property is again very obvious, alpha beta, this is a one scalar, two different scalar, but their product is again a scalar, so we get another quantity, and combinedly we multiply this alpha into beta to beta 1 comma beta 2. On your screen you can see that this multiplication alpha comma alpha into beta, how to multiply to the vector, and you get alpha into beta 1 comma beta 2. And fourth one is a very obvious, so this is a vector space.